So, what happened last time? What did we talk about? Anybody will tell me? Dijkstra's algorithm. No, that's last year. Yeah. Minus pi in 3, yeah. It's so few of you. You shouldn't. You should be quiet. Okay. So we explained Kraskal's algorithm, or the greedy algorithm. What is wrong? You're behaving as if there is something the matter, as if an exam is close or something. I mean, that's so you start, x will in the end be the minus pi in 3, and you do the following. For every edge in order of increasing so we sort the edges. And in order of increasing length, we do the following. If x plus e, if adding this edge to x has no cycle, x gets e. That's it. That's the whole algorithm. And we run the example. Okay, it's remarkable that this simple, no foresight needed algorithm works, and in some sense, it's an attribute to the problem. All right, I mean, it's a very well structured, in some sense, easy problem, the minus pi in 3. Thank God that a few useful problems are easy. Okay, like this one. And it yields to even this unsophisticated myopic approach, okay, the greedy algorithm. And we have to find why, okay? We have to find the reason why. And the reason why is what we call the cut property. If you understand the cut property, you understand the minus pi in 3 problem, all right? That's the only secret it has, all right? It's a very strong property, a very important property, and all algorithms, and there are many that solve the minus pi in 3 problem, they all, in some sense, exploit this property, all right? So what does the cut property say? It's the following. Imagine that we have a this is our x. A set of edges, okay? It divides the graph into many components, all right? Technically, this is called the forest, all right? Why? Because it's a bunch of trees, right? And it's very confusing because a forest is also a subset of a tree, all right? I mean, if you take away a few edges from a tree, you have a forest, right? Which I find confusing, right? So in any event, so what does the cut property say? It says the following: if x is not a mistake, what does it mean for x not to be a mistake? In other words, if in constructing x we never took a really wrong turn, we never really made a mistake, it means that there is a minus pi in 3 containing x. So if X is not a mistake, and E is the shortest edge leaving some component of X, of the graph Vx, strictly speaking, then X plus E is not a mistake. Okay? So, if we have taken not the wrong turn this far, if we have not made a mistake in constructing X, if indeed there is a minimum spanning tree, which you can get by extending X, then extending it by E is good. It's not a mistake. Everybody gets that? It's an if-then statement, so you have to think about it a little, but that's what it says. Let's see why this is the kind of theorem, the kind of mathematical property that immediately you get lots of algorithms out of it, okay? For example, that's why the greedy algorithm works, okay? The cut property says that I can add E as long as it is the shortest edge leaving some component, okay? Right? So I have choices. I can pick this component, this component, this component, this component. Now I picked this component, and E is the shortest edge leaving this component. This means my theorem says that I can add E to what I've been constructing so far. All right? So, why, how is the greedy algorithm an implementation of this theorem? It is because it chooses E not to be the shortest edge leaving some component. It chooses it to be the shortest edge leaving any component, okay? Because it takes the next edge E that has not been considered. It looks to see, does it leave a component? If it leaves a component, certainly it's the shortest edge that leaves this component, okay? If not, they must create a cycle. That's why it checks for cycles. So all I'm saying is that the greedy algorithm, Kruskal's algorithm, is a very simple way of taking advantage of the cut property, okay? There are many more. Any questions? Yeah.
So if in X we have an MST, or say is an MST containing X, why is it that edge E has to be along that same path?
Does not have to be. What do you mean same path?
I'm not phrasing my question. I'll ask you later.
Okay. So basically it says that if X is no mistake, and you pick a component and you look, what is the shortest edge leaving this component? And you decide it's this one, E. Then don't be afraid, add E to X, it's fine, okay? That's what it says. It's like a reassuring theorem, and the algorithm takes advantage in a very explicit way of that, all right? So how do we prove it? And I gave you I sketched the proof before. The proof is really simple. It says, all right, so you tell me that adding E is a mistake, right? This means that you know that there is another minimum spanning tree containing X, okay? So let's say it's this one. That's a minimum spanning tree containing X. It does not contain E. I add E to this minimum spanning tree. I throw E in the soup, okay? What happens? What happens if you have a minimum spanning tree, a tree, and you add an edge to it? A cycle, right? Here's a cycle. This cycle certainly enters this component, touches this component, okay, and leaves it. It enters it by E, it must leave it by some other edge, right? Let's look at this edge. E is the shortest edge leaving this component. So this edge is longer. Therefore, by omitting this edge and throwing in E, I get a better minimum spanning tree. Strictly speaking, I get a minimum spanning tree at least as good, all right, because it could be a tie, right? But still, this negates the objection that E is a mistake. E is not a mistake. There is a minimum spanning tree that contains E, and that's it. Any questions? Yeah. If it leaves a component, it must go to another component, right? So if you have a graph and it's connected components, every edge either is inside a component or it connects to components, right? Make sense? Okay. If you have, so you have to understand that. This is a graph, right? It's a few edges of this graph. Now let's take another edge of the graph. Okay? Maybe this one. This one is inside one component. What is the other possibility? But it connects two components, because one endpoint of the edge must be in some component, and the other endpoint of the edge must be either in a different component or in the same component. If it's not in the same, it has to be in a different component. So maybe it's this, right? An edge has two endpoints. Either the two endpoints are in the same component or they're not. If they're not, then the edge joins two components. Okay? I suspect that you have problem with you have not absorbed as much as we had hoped the concept of a connected component, right? I mean, so make sure you review this. Okay. So this is the cut property. This is why the greedy algorithm is correct. The greedy algorithm is, it's probably the simplest sophisticated algorithm I have written here. Okay, it has the simplest possible pseudocode, but there is a lot of sophistication hidden in what is the only thing. What is the only problem with the greedy algorithm? What is the only thing you have to just stop and think? It's this part, right? How do you look at a graph and an edge, right? I mean, and you decide if it has a cycle or not, and you have to do it in like lightning speed, right? How do you do that? What is the time complexity of the greedy algorithm, of Kraskow's algorithm? Excuse me? So characterize the sort. I don't need to. So we have done sorting. We know how to sort. Okay, but you made a good point that you have to sort the edges, right? So how long does it take to sort the edges? E times log what? V or E? E log V or E log E? Or V? It's the same thing. Remember? E is between n and n squared, okay? So log V and log E is the same thing. Everybody remember that? Everybody with me? Okay? Cool. Plus what? Plus E times the time of the data structure. So we are going to have a data structure that does this operation. If x plus e has no cycle, right? It evaluates this predicate, right? Everybody with me? And what is our goal? What do we want to do? How fast do we want to make this data structure? Log v. Okay, exactly, yeah. So let's see if we can do it. So basically, here's the idea. Here's how I can write this particular data structure maintains connected components of x. All right? So we're going to have a data structure that maintains, what does it mean maintains the, what kind of primitives, what kind of methods do you expect this data structure to have? Find of u. What does it do? It basically gives you the name of the component where you find me u. Which component does it belong? Okay, it returns the right. It returns the So for example, if x plus e has no cycle, imagine that E is uv. It says find of u different for find of e. Okay? So in other words, getting sure that x plus uv does not contain a cycle is the same as saying make sure that u and v are in different components, right? So if you have a data structure, that's fine. And then, of course, we have to take care of this. Once we make sure that there are different components, but we add the edge uv, we have to have something like union of uv, right? Is everybody with me? So all I'm saying is that what we need for this data structure is union and find, okay? This data structure are called union find data structures, yeah?
How hard is it to get the figure out all
This data structure does it for you.
it'll actually generate?
Yes. So all I'm saying is this, that this union find data structure will start with a list of n components, okay? And then it starts building up, okay? Little trees happen, okay? And by unions and finds, all right? So basically what this, if we have union and find, we know how to do this. We all agree? Everybody's with me? That's what we need, union and find. And the question is, so this is a wonderful data structure problem, okay? And it turns out that the best way to do it is through trees. And, but the point is, I know what you are thinking. Trees is a terrible waste, bunch of pointers, parent, left child, right child, who knows what else, right? No, these trees are, they're called trees light, okay? Just one pointer, okay? P. In other words, they are just, for every node, a pointer. Okay? And so where does P of x point? Okay? Here's an idea. Imagine that this is our array of pointers, okay? Imagine that this is our so here is a bunch of, imagine that it's this, a bunch of nodes, a graph with 8 nodes. And here is, okay, this is a possible configuration of the pointer array, okay? Basically, it says, how many components does this graph have? Would you say? 3. It has a component that has the name 2. Why 2? The component always takes the name of one of its nodes, okay? Sort of, you know, one of the node of the component becomes king, okay? Sort of, you know, and there is another one component that has 3, just one node, and then a larger component that called 7, contains 4, 6, 7, 8, right? So that's how it could be done. Let's see, how do we if we have this, how much time does it take to do find? 1, exactly. Okay? Couldn't be that simple, right? I mean, there must be some bad news, okay? How about union? Because basically, if we have union of 1 and 4, okay? Basically, 1 is in component 2, 4 is in component 7. We have to go through everything and make everything, let's say, 7 perhaps, or 2. It depends, okay? We have a choice. Everybody understands? But we have to go through the whole thing, right? So it takes n time to do union. We need a better algorithm. So the question is, can you do it down to log n? Why log n? Because of this. We want this to be log n. Right now it's n. Any questions? So here's the idea. Imagine that instead it is not like that, but it's like this. Okay? Now this is a tree, a real tree, except it's tree light, okay? Because it only needs one pointer. So here's what I mean. You have this. Right? Sorry? Okay, let's say it doesn't. Okay. Thanks. So you see why I'm saying those, call these trees tree light, right? Because there is only one pointer, okay? It goes up. Any questions? Union takes, so union of, let's say, 1 and 2 would do nothing because they are in the same component, but union of 1 and 3 would create a new component, give it the name either 2 or 3, and this component will contain this, and this node, okay? Union merges 2 components. For example, here, union 1 and 3, one way to implement it would be to do this. Okay? Or this. All right? And that's an interesting point. You have a choice here. So let's see. So how do we do find? While P of x not x, do P of x gets P of x, return x. Right? So basically what it does, it says, okay, so you want me to find the component to which 1 belongs, right? Okay? I climb the pointers until I find a node that points to itself. Sorry? Yes. What does it say? It says the following. Have I made a mistake? I climb the chain of pointers. Sorry. What am I doing? Yes, I made a mistake. X gets P of x, I mean. Sorry. I don't change pointers, okay? So what I do with find is I climb the chain of pointers, okay? X initially is 1, then it becomes 2, then it becomes 3, then my predicate is satisfied, I output 3. Everybody with me? So it's very simple to find. Find is very simple, yeah. No, that's not what I wanted. No. Right. Don't confuse us now, okay? Okay, cool. How do you do union? AB. Union AB is as follows. X equals find of A, and B equals Y equals find of B. And then P of X, in other words, what I have done now? I have found the names of the components, the roots of the trees, to which the two nodes A and B belong, okay? I find the root of the tree of A, I find the root of the tree of B, and now I make the former root of one point to the former root of the other, okay? Everybody agrees? This or this? The union. So to find, for example, I had this situation, right? And I wanted to do union of 1 and 3, okay? What is the find of 1? What's the find of 1? What's the find of 3? All right? So my x is 2 and my y is 3. And then I make the pointer of x point to y. Right? And now, these two components are united. If I want to tell me where is 5, pointer jump, 3. Correct answer. Yeah. Okay, good point. Okay. So, strictly speaking, if you think about it, and if you are, as we are in this class, resource conscious, you'll realize that I made a mistake here, okay? I should not make this guy, okay, sort of, you know, the paterfamilias with these huge responsibilities, subservient to this drifter, right? You know what I'm saying? I mean, I should do it the other way around, because this way I'm going to keep the depth as little as possible, right? So I have to insert a little code here, which is depth conscious, okay? Which remembers the depths of the tree. All right, so here's how I do it. I say, if depth of x less than depth of y, then p of x equals y. Then, of course, then I make x child of y, because it's of lesser depth. Else, p of y equals x. And now I have to do something clever. If depth of x equals depth of y, depth of x is incremented by 1. Okay? You get it? All right? I make the smaller tree point to the larger tree. What happens, smaller in the sense of, in terms of depth, right? What happens if these trees, if the depths are equal? Then I still have to make one point to the other, but now the other's depth is incremented. Okay, because two trees of the same depth collided, and a tree of greater depth emerged. Everybody sees that? So that's the code. That's the code for union. Instead of naively picking one and making it the parent, I choose the parent to be the one with greater depth. And if both roots have the same depth, then I still make one of them the parent of the other, but then I increase its depth because its depth has increased. Everybody sees that? That's it, that's the code. And this code is log n. Let's see why. Okay? Why is this log n? Okay, here is y log n. Anybody can tell me why log n? Because if a tree has depth d, then it must have at least 2 to the d vertices. Right? If I prove this, I've proved it. Because d then cannot be bigger than log n, because I only have n vertices. Right? Is everybody with me? So I have to prove you this. I have to prove this to you. Really easy. Okay? really like second week of 70. Easy.
Right. How come like a linked list of length 3, would that still count as 3? Because that wouldn't have like 6 vertices.
Say again.
So linked list in depth 3.
Right.
Would that count?
It would never happen.
It just won't happen.
It will not happen. Yeah. Okay? So it's really second week of 70, okay? Induction. True if depth d equals 0, okay? D equals 0 is when we all start, right? All right? There is one node in every tree, in every component. The depth is 0, and there is at most one node, okay? End of story. Everybody with me? And if it happens, suppose it happens for k plus 1. How did this tree get depth k plus 1? It was the collision of two trees of depth k. Are the union of two trees of depth k. And therefore, 2 to the k plus 2 to the k equals 2 to the k plus 1, and we're done. Okay? End of proof. All right? So this simple trick, in other words, always remember the depth, okay? You know, every trick in data structures represents a commitment, okay? Now we have to have a separate array that says depth, okay? Okay. So you remember the depth, and every time you have to union two trees, you link the one with lesser depth to the one with greater depth, okay? And if they have equal depth, you don't forget to increment the depth of the new root. Yes? No, unfortunately, we will give you the depth of the node you are looking at. Okay. Okay, you can't do that. Okay, you have to remember the depth. Think about it. Any more questions? Okay, so that does it. So now I'll tell you what my friend there was talking about before. An incredible hack, okay? A beautiful data structures hack, okay? And it's not only a hack, it's also the beginning of a beautiful mathematical story. The mathematical story you can find in the book, okay? Now I'll just tell you the hack and what it does for you, okay? So here is the hack. Imagine that you are in this situation. I don't know. Okay? You have done fine. You started from here. Okay? You sweated your way all the way to 8, 7, and then you said, okay, 7, found it, all right? And next time they will say, okay, now what's the find of this? And you say, okay, all right, okay. What's the find of this? Okay, you need it again. All right, that's stupid, okay? You should be able to help yourself, okay? So you know so much. I mean, you have been in so many places. You should have learned something, okay? What have you learned? You have learned, once you did this, you have learned that you can telescope these pointers, right? Get it? Do you see what I mean? As you go up, you remember your pointers, and then you set them to the path. In other words, next time you want the parent, or the component of this, don't go through the long chain. Go directly here. If you want the parent of this, go here and then directly there. So this way you reuse you use your knowledge, what you have learned by going through these trees and by sweating your way up all these uphill paths. Okay? Everybody with me? Okay, so that's easy to do. It at most doubles the time it takes to do a find. Everybody sees that? Sorry? Twice. So you do it once, and then you do it once more, but you remember where you have to put all pointers. Okay? It's the same, right? So, except that, now things are a little better, okay? So, this is called, this has a name, this hack has a name. What's the name? Path, it's in the book, I forget. Not telescoping. Sorry? Path compression, yes. Union find with path compression. So what's so good about it? Okay? Still log n in the worst case. Okay? Except that it has the following amazing property. N unions and finds cost a total of order of n. It should be n log n because each one of them is log n in the worst case, right? Well, it turns out the worst case happens rarely, and there are often a lot of best cases. So, cost total of order of n. You get it? So, you have the union find data structure. You do the root trick, okay? The depth trick. Always link the root of lesser depth to the root of greater depth, okay? This brings you down from n, worst case n, to worst case log n. You do path compression, and your worst case of your data structure still stays n log n. But the amazing thing is, okay, that overall, on the average, your union finds cost you 1. Okay? Any questions? That's a wonderful result, yeah, Alex?
So isn't O of n worse than log n?
Not. It's, you do n data structure operations and costs you n. It should be n log n, right? Yeah. Right. I'll talk about that. Yeah. Any questions? So, as your colleague is saying, it's not exactly, I've been lying to you, okay? It's not exactly n. It's something called n alpha of n. What is alpha of n? Is it log n? No. Is it log n? No. What is it? What is log n, first of all, right? Do you know what log n is? is the log of log n, I know that. What is log n? Think. It's 5. Log n is 5. Okay? How big is the web, okay? How many humans are there in the world, okay? About 2 to the 32, right? Okay? Take the log, 8. Oh, sorry. Take the log of 32, 5, right? You see what I'm saying? Take the log once, you get 32. Take the log again, 5. So unless you have a database that has more lines than there are people in the universe, okay, maybe you have a database that has as many lines as there are documents in the web, right? Which is more than 232. Or maybe you have a database which has as many lines as there are characters in the web. Okay, 6. Right? You see my point? So log n is 6. Alpha of n is 4. Okay? It's even smaller than it's even smaller than log n. Okay? So my point is, it's really not a constant, but I mean, believe me, if you stay in this planet, it's going to be a constant, okay? All right? Any questions? Yeah. Yes, yes. You have to do both tricks, both the depth trick and the path compression. Okay? Now, to prove this is a wonderful exercise. And it's a very nice, I mean, if you are interested in math, it's a very nice mathematical exercise, and I totally recommend that you do it, that you read it. It's in the book. It's 2.5 pages in the book. It's not huge, okay? Just you know, it's a very nice, it's not, you know, don't worry, it's not in the midterm, all right? Today's lecture is in the midterm. Thursday's lecture is not. Thursdays we are going to talk about parallel algorithms for all this. Okay? But it's going to be for the next midterm. Okay. Cool. So yeah. Path. What does it do? So I did not write the code, but what it does is the following. Every time you do a find, and this entails following a tree up to the root, all these nodes in the tree, you make them sons directly of the root. You make them point to the root, so that next time you save time. That's path compression. You compress the path to length 1, all these paths. Yeah, no, you don't add pointers, you change the pointers, right? I mean, instead, don't point there directly, okay? Because anytime you'll be here, you'll go there directly, okay? So, because that's where you want to go. That completely changes the depth, yes, right. I mean, so it becomes very, on the average, constant, okay? Cool. All right. So I've been telling you that there are many algorithms for the minimum spanning tree. Incidentally, there is a paper, I'm sure you can find on the web, that tells you the history of the minimum spanning tree problem, all right? So Kraskal's algorithm was known well before Kraskal, okay? Some people used to call it Edmond's algorithm, another mathematician. And then somebody said, wait a minute, that's not Edmond's algorithm, it's Kraskal's algorithm. And everybody started calling Kraskal's algorithm. And then somebody said, no, it's somebody, you know, some blighter whose name never became known in England had found it before, okay? And the same for the, you know, the algorithm that I'm going to tell you now is called Prim's algorithm. But Prim, I mean, here is a good story. Prim was a researcher in Bell Labs, and sort of, you know, they were having, they were competing with IBM. I mean, that was before your time, okay? The greatest companies, okay? The big evil computer companies, okay? They were IBM and Bell and AT&T, okay? So, you know, these were, all right? And they were fighting, all right? They were competing. And because they both had networks, okay? Networks of telephone, wires, chips, and all that, they were both very interested in the medium spanning tree. And apparently, there is an internal memo of IBM that says that, unfortunately, this problem is too difficult to solve by computer. Okay, so, you know, so you know, they had been treated the medium spanning tree as something that you need to have humans look at the tree and sort of construct it. Okay, so, you know, it's amazing that these humans had not thought of the algorithm. Okay. In any event, Prim was the if you didn't get it, this is our intermission. Okay, so, you know, you are feel free to stretch. All right, I mean, we are this is break time. So so Prim was this high-level researcher at Bell Labs and came up with this algorithm. And boy, was everybody impressed. Okay, so, you know, and so internally, AT&T was doing it much faster than IBM, right? I mean, so for a couple of years they had an advantage. The funny thing is that Prim, this algorithm was well known, and it had been published, okay, in a paper a few years before. Except that this paper had a famous result in the beginning, and so nobody read the last paragraph of the paper, okay? So, and I'll show you the algorithm and you'll see why. Okay? So let's see. Remember, I'm going to give you another algorithm for medium spanning tree. Of course, I'm going to use the cut property, right? The same theorem. And so what will be the nature of my algorithm? So what's the difference? The point is that the greedy algorithm, Kraskal's algorithm, takes a very special kind of advantage of the cut property. Basically, it does not pick a component and then pick the shortest edge out of this component. It just picks the shortest edge out of any component, right? That's what it does. All right, so let's see how we can do it differently. For example, how about Kraskal. E is shortest edge out of any connected component. Prim. E is shortest edge out of the connected component of S. Okay? So, here's the story. There is a special node, call it S. Why is it special? No reason. This is S. Okay? So, sorry. So maybe for these 5 minutes you want to move here. Okay. So here's my point. Why, you know, Kraskal's algorithm would start here, right? No, I'm very partial to S. Okay? All right, so I take the shortest edge out of S. What's that? 4, okay, cool. Now I'm taking the shortest edge out of the component of S. 1. Now I take the shortest edge out of the component of S. You see how I'm doing? I'm growing my tree this way. Then what? Then? Right. We're done, right? Think about it. This is the minimum spanning tree, right? And you got it this way. How do you know this and that this is a correct algorithm? The cut property, okay? It just takes advantage in a slightly different way, in a one-sided way of the cut property. So what? When I write you want me to write the code for this? When I write the code for this, I think you are in for a surprise. Anybody can guess? What is the code for this? I'll write pseudocode for this algorithm. All right. So let's see who gets it first as I write the code. So initialize Now do you get it? It's Dijkstra's algorithm. If you add here it's exactly Dijkstra's algorithm. But you don't, okay? And the famous paper I mentioned is Dijkstra's paper. Okay, the guy was solving the minimum spanning tree also, but nobody read past page 2, you know what I'm saying? And his paper, the title of his paper, is on two problems in connection with graphs, okay? So that's a big hint, okay, that there is something else here, okay? Do you get it? That's an amazing observation. That both the minimum spanning tree and shortest paths, basically they are exactly the same. You see what's the difference? What's the difference? The difference is very slight. That the shortest path problem wants you to construct a shortest path tree, okay? The shortest path tree should contain all shortest paths from S to all nodes in the graph. This one wants you to construct a minimum spanning tree, okay? The best way to connect the nodes of the graph. And these two could be different. You see why these could be different? Do you understand? So let's make a simple example. You won't find it here, I believe, right? But let's see. Right? Let's see. Right. So the tree now would not have this, right? The minimum spanning tree would not have this, would have this. Everybody sees that? But this is the best tree for Dijkstra, for shortest paths. So you see what I've done here? I've constructed an example where the two solutions differ. If you want to find the shortest paths from S to everything, you would not do that. Okay, you would have this. This is the shortest path from here to there. Right? But if you want to find the shortest way to connect, definitely you should do this. Right? Yeah.
Would a minimum spanning tree really take us towards, or like why wouldn't the minimum spanning tree? Oh, okay, never mind.
Right? Right. Everybody understands what I'm saying? I mean, there is a subtle difference between minimum spanning tree and yeah. The minimum spanning tree will take the two. That's the minimum spanning tree. Here. But Dijkstra's algorithm, okay, we'll do this. Dijkstra's shortest path algorithm. Okay, we'll tell you if you want to go from here to there, you should, right? I mean, imagine that this was S, okay? You better go this way, right? Not that way. Yeah.
So the slots do cycle checking, right?
Sorry?
The slots do cycle checking, right? Cycle checking to check if it's going to form a cycle.
So this does not, this does not need to do anything. So it just, no, it does not need to do anything. You just run Dijkstra, and you delete 7 characters. Okay. That gives you the same algorithm, an algorithm for minimum spanning tree, which for some reason is called Prim's algorithm. Okay. Finally, are you ready for this? Here is, so I told you that people have been, historians of algorithms have been looking back to find out who was the first who thought about the minimum spanning tree algorithm, okay? And surprisingly, they didn't find a Greek who had but they found somebody in 1919, okay? So, the beginning of the last century. A Czech guy called Borůvka, okay? Who was an electrical engineer, a Czech electrical engineer. He was eager to optimize his company's grid, and therefore he came up with an algorithm for the minimum spanning tree. And did he take advantage of the cut property? Of course he did, okay? And he did it in a different way, completely different way, all right? Again, Kraskal's algorithm, what does that for you? It adds always the shortest edge out of any component. Prim's algorithm adds the shortest edge out of the component that contains S, okay? It's partial to some node S. All right. How about Borůvka's algorithm? I don't think you're ready for this, okay? Borůvka's algorithm adds all edges out of all components at the same time. Complete chaos. All right? Can you visualize that? So, why would Why, you know, can this have any advantage? What do you think? Sorry? Better? Parallelized, yes. That's exactly it, thanks, yeah. This one is better algorithm for parallel, okay? That's, you know, what we're going to do next is a bunch of observations about parallel algorithms for these problems, for shortest path, and minimum spanning tree. But the point is that you have to be a little careful, all right? Imagine that you have a graph. So the point is you have a graph or components, okay? And you say, what is the shortest edge out of this? This one. What is the shortest edge out of this? This one. What is the shortest edge out of this? This one. What is the shortest edge? So that's the same. So basically, what's the shortest edge out of this? This one. What's the shortest edge out of this? This one. What's the shortest edge out of this? This one. And so on. What's the shortest edge out of this? This one. Okay? So in one fell swoop, you have two components, right? And then what do? You have to do something to merge those. And then one more pass and you're done. Doesn't this sound like the perfect parallel algorithm? Yeah. Sorry? Ah, good, excellent question. So what can go wrong, all right? Here's what can go wrong. What is the shortest edge out of this? Is this one. It has length 6. What is the shortest edge out of this? It's this one. It also happens to have length 6. 6, 6. Can happen, right? If you have a cycle of equal length, you are in trouble. So that's why, before starting running actually any minimum spanning tree algorithm, why don't you change the lengths? Make these 601s, this 602, this 603, this 604, okay? Nothing else will change, right? And now you have no, you get it? Now you have no ties, right? Therefore, this will choose this one and not this one. This may choose this one. This will choose this one. This will choose, okay? So it's not going to be no cycles. Am I clear? If there are no ties, no cycles. Okay? So, just a trivial preprocessing. Go through the edges and make them all different, okay? In a way that will not affect the essence of the algorithm. All right? And now you can run the new algorithm by Boruvka. So what is this algorithm? It's the following. Incidentally, anybody can tell me, it says what? It says that in the beginning x equals empty, then make all edge lengths different. And then it says the following. Repeat until there is only one connected component. For each connected component C, add to X the shortest edge out of C. And then find the connected components of the new X. So, in other words, you start with every node in a separate component. After one pass, you started with n components. How many components are you going to have after one pass? At most n over 2. Everybody understands that? Because every node will at least have another, okay? Maybe 3, maybe 4, who knows, okay? But at least one another. Therefore, the number of components is going to be at least halved, okay? Divided by 2 at least. So how many iterations is there going to be? That's what you want to hear for every parallel algorithm, right? Log n. That's music. You know, if you think about it, the other algorithms are dead in the water for parallelism. Okay? Because the first one talks about first of all, it sorts the edges and processes each one of them. It's extremely sequential, right? I mean, its cleverness lies in that it has sorted the edges and processes them one after the other sequentially. All right? Sorry? So, right, okay, we'll talk about that. The second algorithm, Prim's algorithm, is also very sequential, okay? It starts with a queue, and it deletes means elements for the queue. They're both extremely sequential, okay? And if you think about it, no matter how cleverly, I mean, even if you had done it in any other way, if this is your minimum spanning tree, suppose that you have a graph with 1,000 nodes, and the minimum spanning tree happens to be a path. It's possible, right? You need something like that to find it fast. No matter how clever your algorithm is, if it doesn't do things in parallel like this, like Borufka's algorithm, right? Incidentally, Borufka's algorithm is not in the book, and with any luck, by the end of next week, I'll give you some notes about Borufka's algorithm, okay? Is everybody with me? So, all I'm saying is that all these algorithms we have seen before, they are dead in the water when it comes to parallelism. And the reason is not their implementation because they chose the wrong data structure. The reason is that if your path, if your minimum spanning tree happens to be a path, then you need something like Borufka, at least, in order to find it in less than n time, okay? You realize that n time is terrible for parallel. I mean, when you are doing a parallel algorithms, we are extremely ambitious. We are going for something like log n. All right? Okay, so again, this is Borufka's algorithm. It is the algorithm of choice when we are interested in parallelism, when we have parallel processors on our chip. And that's what we are going to analyze on Thursday, I guess. Everybody knows that we have a midterm when. Next. Cool. And what else? We have a review session when? It has not. So there's going to be a review session sometime the weekend, I believe Sunday afternoon. There are going to be also, wait, there are going to be also extra office hours by everybody, all right?